All right, so we're going to find the area bounded by these two curves. And one of them we know is a parabola. And the other guy is just a line. The issue here is that we said if x is isolated, you do a dy problem. And if y is isolated, you do a dx problem. In this one, you kind of have a combination of the two. But we do know that this parabola, if I were to isolate x, it would be easier, right? So I would have 4x minus y squared equals x minus y squared over 4. And we know this is a parabola that opens to the left. And if I isolate y, I would have a positive and a negative square root, which is still okay. That would be y isolated, but then I would have two pieces to work with. So it's probably easier just to isolate x in both of them and do a dy problem. Let's isolate x here too. So I have y minus 4 equals 2x. And if I divide by 2, I have x equals y minus 4 over 2. And since this is not a function, it doesn't pass the vertical line test, I'm not going to even bother putting it in my TI. I could put it as a top and a bottom piece, and this is just a line. We know what y equals mx plus b looks like. I'm going to go for limits of integration. Like we said, we're going to need the intersection point. So I'll get the intersection points and then get an idea of what the graph looks like, which I already know this one has a sideways parabola going on. And this one, so let's do this one in black. And we'll do this guy in red so we can distinguish top and bottom. That has a y-intercept of 4 and a slope that's positive, so it'll look something like that. So the area bounded is right here. And even from the graph, we can tell that it probably won't be a good idea to do a dx problem, because if I do a dx problem, my top is red and my bottom is black here. But when I get to this edge, my top is black and my bottom is black. So I'm going to have to split my parabola into two pieces. So why bother with that? It's definitely easier if I just go and stack up my rectangles vertically. That way my right is always touching the black and my left is always touching the red. And it's clear cut. Right is always black throughout the entire curve or throughout the entire region, and left is always in red. It's going to be confusing. Let me put right in black and left is in red. No matter where I go, even if I go up here, left is in red, right side is in black. So definitely it looks like I'm stacking up my rectangles vertically, and a dy problem would be good. I just need to get my limits of integration to know from where to where I'm stacking them up. So my area bounded will be right minus left, my right hand on the right, and then left side, whatever function it is, dy. These guys are the things I'm trying to get. My right is always my parabola, so it's negative y squared over 4. My parabola right here, where the x is isolated. My left edge of the graph is always red, which is the line. Make sure you put it in terms of y because you're doing a dy problem. So make sure you don't mix and match. Don't put y equals 2x plus 4 in here. Because you're doing a dy problem, your entire integrand should be in terms of y's, and your limits of integration should also be y's. So We got our sideways parabola, we got our line, we decided to do a dy problem and isolate x because it was easy to isolate x in both of them. Now let's go get limits of integration by finding the intersection points. So to find the intersection points, I guess I'll just set my two equal. Different ways you can go about it. I'm going to set my x's equal to each other. And maybe we'll cross multiply and get negative 2y squared equals 4, y minus 4, so negative 2y squared, 4y minus 16. Let me move everything to that side, 2y squared plus 4y minus 16. Let's divide everybody by 2, make the numbers smaller. Y squared plus 2y minus 8. That looks factorable. Y plus 4, y minus 2. So intersection points are negative 4 for my y value and positive 4 for my, or positive 2 for my y value. And because I need y values, I won't even care and go find the corresponding x values because I have a good enough sketch going on. So here is my lower bound. That's a y value of negative 4. And then my upper limit is a y value of 2. That's how I'm stacking up my rectangles from bottom to top. So I have negative 4 to positive 2. And that's my integral. Let's go use our TI to calculate what that area would be. Again, it's just a power function. I can distribute, combine like terms, and do the integration by hand. But we can go punch it in our TI and practice how to use our TI to get the area. So let me get it to fit the window. So our function, or my integrand, that's all I care about is integration, right? So I'm going to do math 9. And let's see what my integrand is. Oh, I don't want it in y equals. Let me quit that. Math 9. Bottom limit negative 4. Top limit 2. My function is negative x squared or y squared. Doesn't matter. You're putting here. Oh, divided by 4. And then minus, I'm going to put parentheses for that other thing. X minus 4, close parentheses, divide that by 2. And dx. So don't let the dx and dy confuse you here. By the time you get the area function and you do your right minus left, you did a dy problem and stacked it up vertically, but at the end of the day, whatever variable you use to integrate on your TI doesn't matter. So hopefully I haven't left out any parentheses. We're going to push enter. And it looks like once we do that power function integration, we're going to get an area enclosed of 9 units squared. And that's it for that example.